formation from outer disk rotation curves at redshift 0.6 to 2.5.
Thank you, Diana. I'm just waiting for another second. Okay, so this is an observational talk. It's about high redshift, about main sequence galaxies, and using them to try to experimentally probe the halos through rotation curves. Of course, a field which is very, very well developed at 0 redshift has a bad reputation. Stefan, is that right? Has a very good reputation. And I'll tell you what we've been doing on it. We had 2 years ago a set of papers on this for our first try, and this is sort of the second generation of the work. So as you know, there's various ways to go about it observationally to try to determine how much dark matter you actually have in a galaxy. The easiest one is, at least for star-forming galaxies, if you have gas in a star-forming galaxy in rotation, and then you go ahead and measure the rotation peak at the peak of the rotation curve near RE, R1/2, if that's correct. The amplitude corrected for inclination, and from that you get a dynamical mass. That one you compare with the stellar mass from photometry and modeling. And in these star-forming galaxies at high redshift, you have to add the molecular mass, because that's typically 30 to 50% of the component. So that's easy, but it's of course also fraught with what low redshift people call M/L ratio problems, in that you may not have the model right, the IMF may not be correct. Although note, if you have 50% gas fractions, the problem with the notorious problem with the IMF is only half as bad as they are at low redshift. Lensing. Perhaps many people consider that the best technique, the highest accuracy technique, but at least as far as I know, for the main sequence population at redshift 1 to 2.5, there's so few background galaxies to do galaxy lensing. The next one are rotation curves, just like at low redshift. Now there, you can use H-alpha, that's what we've been doing, or CO, that's what we'll be doing as well. There is, as we know from low redshift, one problem is as you go out, the metallicity decreases. That means both the CO signals go down, the star formation rate changes, surface brightness goes down. So it gets very, very difficult very quickly. And so at low redshift, the technique of choice is H1. We don't have that, and we won't have it. Okay? Even with SKA, forget it. What we are doing here, you will not see done at redshift 2 in 15 years from now, I'm fairly sure. Outer halo tracers, satellite kinematics, et cetera. In principle, yes, but not quite yet. I think we are beginning to look into this now. Problem is the numbers of such objects, and then of course their brightnesses, and getting all the redshifts right, and so forth. It's a beginning field. I'm sure with the big telescopes of the next generation, that will be a technique. Tully-Fisher offset, we've done that. And other people have done it too, and unfortunately, depending on the biases of your sample, et cetera, the results often are quite contradictory. So unfortunately, that's not so good. Z-scale height, according to Couture et al., that's one of the prime methods you should use. For that, you need to have the scale height in the outer part of the galaxy in stars or in mass. And then you measure the velocity dispersion. Well, of course, you immediately see that there's a problem there. You can't do that in the same galaxy, because in Edgeon system, you would have to rely on the isotropy of the velocity dispersion, which actually is at high redshift not as bad as at low redshift. Now, that can be done, and we are doing it, but I won't show it here. It's still it's fraught with some uncertainties. So what I will do today is tell you about the progress of our work here on the individual rotation curves. Stacked rotation curves can be done as well, but again, the trick is how to normalize different galaxies and how you do that specifically. There are 2 papers out, Lang et al. From 2017 with about 100 galaxies, and then Tiley 2018, and they agree if they use the same technology, but if they use different technologies, you get different results. So that's also unfortunately tricky. All of this is actually tricky. All right, so what did we do at the time with the single objects? Well, we took some massive galaxies at redshift 2, typically in stars near 10 to the 11th, so near the Schechter mass, and then measured with the integral field unit symphony and adaptive optics, the 2-dimensional velocity distribution, and then extracted the 1D field. Question many people ask, why don't you use the 2-dimensional velocity field? You can do that, we've done that. You don't gain much additional information on the rotation curves. You can gain some information on the inclination, but not on the rotation curve. So this is, if you like, as if you had a slit going through the galaxy along the major axis. Here is the velocity dispersion, and here is the distribution of H alpha light. Now note, the first thing you have to know at high redshift is these galaxies are small. They are, a few arc seconds across. Even with adaptive optics, you can't get better than about 0.2 arc seconds. So much of what you see here in the inner parts of the galaxy is heavily affected by beam smearing. So you have to make forward models. So what you do, or what we do, is we assume that there is a compact bulge unresolved, then an exponential disk, and then an NFW halo with a concentration parameter which you can take from the literature. We take John Bullock's paper from 2001. Then you make, in this forward modeling, you take into account the beam smearing, and then you use Bayesian techniques to sample the plane with priors set on the size from HST imagery, and of course the stellar masses, gas masses, either from direct observations of CO, if you have that, or from scaling relations. And then the velocity dispersion comes from measurements in the outer disk. That's very important. In contrast to low redshift systems, these high redshift systems are dispersion challenged. And even those which are rotating have a V over sigma of 4 that you need to take into account as there arises in the Jeans equation a pressure term which for an exponential disk gets larger and larger as you go to the outside. So without that you cannot get a result. So then if you fold the rotation curve, then the direct fit of this forward model would give you this thing here. So that's actually, much of that is due to this asymmetric drift. So the intrinsic VC of the baryonic disk is this one. It's still dropping. And then if you correct for the bulge and everything else in the dark matter, then you get, this is the over rotation curve. So you cannot possibly read off the result from this picture. I'm saying this because there are colleagues who are experts in the field and write blogs where they then basically draw straight lines on the pictures. This is insulting, sorry to say. I mean, one shouldn't really do this. This is the situation we are in at high redshift. Now, from these 6 early galaxies, I'll tell you briefly in a second what we found. We have now, in the last 2 years, gone from 6 to 40. With Symphony, with KMOS, with the NOEMA millimeter interferometer, and then this is basically a combination. We do pretty well in terms of sampling in redshift, in the different redshift slices available to us. The main sequence, although we're a little biased above it, of course, we are not deliberately, we are deliberately biased in terms of size. Why? Well, because we need to resolve the object. So if you take what you would call the blue nuggets, there's no chance to get a rotation curve on that. So I'm sorry, we have to go to the big objects. That has one advantage. And I'll show you this. None of the results I'll show you are just effects of varying sizes. So the smaller objects are basically more baryon dominated or something like that. That's not the case. Basically have more or less one size for all the objects. Okay, so here's just a selection out of the 40, so you can see a little bit better what the quality of the data is. Now, in the first Nature paper, 2017, unfortunately, most people only heard falling rotation curves. Only for, if you look in the abstract, it says that, but it says, which is caused by a combination of asymmetric, but that was difficult. It was falling rotation curves. And then the next reaction is sort of the knee-jerk thing from the theory community was nonsense. Cannot be. Bullshit. So as we now have many more, I can tell you we keep finding the same result in a more robust fashion, but we actually are finding rising rotation curves, okay, or flat ones, okay, to the extent we can tell. So as we have a larger sample, we are more fairly sampling all the various galaxies, and here on top of each other you can see you get almost as much of a rich variety as in Sofue's annual reviews paper. So, but yes, there are falling rotation curves. So now let me jump into the results right away, since there is little time. So what did we find in 2017? We found that there are, of the 6 objects, 5, and in particular the ones at the highest redshift, which have very high baryon masses, as I said, near the Schechter mass, also very large bulges, so a bulge to total between 0.4 and 0.8, but large, as I said, with a very low dark matter fraction. Of course, we all know how difficult it is to really nail down the numbers. Typically, the errors in F dark matter in the Bayesian MC is a plus minus 8 to 15%, okay? So the average values of these objects here are less than 10%. And many people didn't like that, okay? So it's good, we need to check that. So we have, and so the new sample at redshift 2 looks like that. Okay, so we see, number 1, yes, there is a majority of objects in this high baryon mass, high bulge mass, corner with low dark matter fractions. But there are some others, including high dark matter objects, but slightly lower mass. So that's redshift from about 1.5 to 2.5. So that's the high redshift tail. Now we know from Stefan's papers and others that as you go to redshift 0 for these kind of masses, you would expect dark matter fractions at 50% or higher. So yeah, there are some, but not many. But indeed, when we go from redshift 2 to redshift 1, we will see in a second, we do see higher dark matter fractions. Now it's interesting to look at those objects here at high redshift, which do have high dark matter fractions. They are rings. We heard earlier today about rings. These are apparently hollow H-alpha rings, big things. This guy has an RE of 7 kiloparsecs. This 6 kiloparsecs. Now I cannot vouch that there is not a big black hole in the center or a highly column density obscured object. That we cannot exclude, and this is something which we will all discover in the next years as the millimeter interferometry will come in. The columns of dust we're talking about in the centers of these objects are like in up to 20. So you could hide a lot of material. But they look empty, and that would be sort of maybe a situation which you might expect early on. Now, without exception, the objects down in here look like this. Big bulge, AGN active in some cases, with sort of a ring around it. I only show one of many pictures. Now, let's go now to redshift below 1. These are the blue objects. Now there are many more objects up here, and all the objects which are in the high dark matter fraction regime at redshift between 0.6 and 1.2 look like, well, this is what you would call NGC 891 or something like this, okay? So they do have bulges. and then there is sort of big disks draped around them. So the trend is, and that is also what Stein-Voits found from the inner disk analysis of many more objects. At highest redshift, you find many more of these low dark matter fraction, high mass objects, and at low redshift, the population on the same sequence in this three-dimensional hyperplane moves up to higher dark matter fractions. Now you can ask about other parameters. What are the other parameters? I told you already that the sizes, basically we have one size. Okay? This is not a size effect. It is a little bit a lambda effect in that, yes, indeed, the smallest lambda objects are more compact, and therefore then you could see a dark matter dependence. The baryonic dependence you've already seen. The strongest dependence statistically is the sigma 1, what Sandy called sigma 1, or sigma baryon. This is sigma baryon over RE, but if I would plot sigma 1, we would find the same thing. That's the strongest correlation. So with other words, here this is again the same thing in these two domains. We seem to be having objects, particularly at high redshift, where the high central surface density on a kiloparsec scale knows about the dark matter fraction at 6 kiloparsecs, and vice versa. Okay? So, lest you were a joker if you think there might be a reason for that. And so, how does that potentially connect up to low redshift? I would argue pretty well, because we see the descendants of these objects. These descendants of these objects is not the Milky Way, it is not Andromeda. These are ETGs, early type galaxies. So let's look first at the green ones here. That's in this mass range, that's the Atlas 3D early type sample. And you see they're basically, with a saltpeter IMF, which is their preference, fall in exactly the same region. Then we have a new sample from Mendel et al., which is a KMOS sample at redshift 1.4 to 2, also early type galaxies. So they also could be descendants. They are on that side. And then finally, there are the disks of McGough, and he always insists it's all surface density. Yes, that's right, but it's set up at the very highest redshift. Now note, the difference between here and here is easy to understand. That's just size, because these are red nuggets. And the size typically is about 2.5 square. That gives you the effect from here to here. Effect from here to lower redshift could be either or combined in combination the gas fractions and at the same time, again, the size. So that objects would find themselves at later times over here when they started here is also reasonable. So I would argue this story holds up also if you look at the local redshift or mid-redshift samples, and not only disk galaxies, but also early type galaxies. So what is it? What are we talking about? This word dark matter fraction means that from this rotation curve, we allow where we measure here at 1 or a few, I mean we can go out further, but we set the bar here at 1, the dark matter fraction is 0.07. Well, the halo, the NFW halo, which would fit that, is this halo. Well, that has an MD at halo scale of baryons over dark matter of about 3. That's nonsense. So we're not talking about the total dark matter fraction. We're talking about the local dark matter fraction. So that means there must be a process which removes, relative to NFW, material. And we can express that in terms of the slope. So if we vary the NFW slope, which in the inner part is 1, and fit now not for the dark matter fraction, but instead for the slope, then the dark matter fraction, low dark matter fractions, means very shallow slopes, essentially a core. So I would phrase, therefore, the physical result we have. At high redshift, there seem to be fast processes which take galaxies which are very massive and about to quench, probably build black holes at that time, drive, because of the short time scales of bringing gas into the center, compaction, gas into the center, and through processes which could be dynamical friction plus outflows, drive dark matter out and become baryonically dominated. Thank you.
Thank you, Reinhard. I have a little gift for you for being on time.
Thank you.
Do we have any questions for Reinhard? Yes.
How do you drive the dark matter out?
Andy. Where's Andy?
Now you can't take gas in and blow it out again, then dark matter will be accessed again and it doesn't help. You have to bring the gas slowly into the dynamic cold core of an NWA. The problem then is the gas is in, the baryons are in, and due to the additional heat in your potential well, you don't get the core again. But if you then blow out 50%, let's say, of the baryons, because the dark halo has been heated, you remove the dark core at the cusp in your form core. That works. So slow infall, heating of the dark matter, blowing out 50% of the baryons, relaxes the low potential well, and you get the core. That is the best mode you could find at the moment.
Susan.
So I'm kind of concerned about systematics. Aside from the whole assumptions about molecular gas as a function of mass and redshift, there's also the problem of deriving a stellar mass from different wave bands. So if I was to say measure stellar mass from waveband A, B, C, and then I was to measure stellar mass from A prime, C, and D, we'll get a different number. So K corrections, and then also just simply using different wave bands.
Yeah, Susan, okay, we are using these constraints, that's the advantage of this technique, only as broad priors, either flat-topped or with a sigma, which is 0.4 dex, okay? So that's very, very soft priors. Okay, this technique is not, so to speak, fraught by M/L ratios so much, yeah? Because we're using the shape of the rotation curve. I mean, if you play with forward modeling to get at this redshift a rotation curve which does that, there's hardly any way you get dark matter in there, in any numbers. Now, there's also an advantage, which, if you give me 20 seconds, relative to the low redshift universe. There's the famous disk halo conspiracy, right? That says if you have a flat rotation curve, you can, break that apart in various ways. Not so easy at high redshift if indeed the halo concentration parameters decrease. Because that means, on the one hand, you drive in the baryons very efficiently, so you get a lot of baryons. And at the same time, the dark matter halo before adiabatic contraction is actually, by nature, further out. Okay, so you cannot get easily these flat rotation curves as a low redshift. You can, but not as easily. Now, the adiabatic contraction is certainly an issue. We are actually using it, and they typically tend to increase the fractions, the dark matter fractions, by 5 to 10% up, okay, as you would expect. But it's not dramatic. Have you not heard what I said? I said there is a big difference, and I would ask you please to then check it yourself. If you go from a concentration parameter of 10 to a concentration parameter of 4, that's a dramatic effect on the halo shape relative to the baryons.
All right, thank you, Reinhard. Let's thank him again.
Right.